we represent these trees in different ways. For example, the world tree, each node can have a huge number of children. Right? So USA has 50 states, District of Columbia, Puerto Rico, and a few other little subjugated islands still. So 55 or so nodes, and each of those has a bazillion nodes. In the binary tree, we say, again, there's only 2 nodes, and so instead of having a selector called children, we have a selector called left child and a selector called right child. Okay? Sorry. Okay, so that's what a tree is. That's the general idea of trees. I haven't shown you any actual code yet. I'll get to that in a minute. What I want to do first is talk about the idea of a node. And a node is basically a piece of a tree. So this node represents the United States. The node is not just the datum USA. Sorry, it's the chalk dust. The USA node is this whole thing. It's the datum, the value, USA, plus all the children and grandchildren and grand-grandchildren and so on of this node, okay? So, what's the difference between a node and a tree? Come on, no hands at all. A tree is a bunch of nodes connected. Well, but this node is a bunch of nodes connected, too. Somebody, yeah. Okay, he's saying a node is part of a tree, and a tree doesn't have a parent. It's not part of anything else. Well, that could be, except what I didn't tell you, if only I could find my chalk, is that there's this tree called solar system, and it also has nodes Venus and Mars and so on. So has this just stopped being a tree? Okay, so it's a trick question. The answer is there is no difference. A tree is just a node that we happen to be thinking of as the thing that we're looking at right now, the important collection. I'm emphasizing this because data structures textbooks almost always get this wrong. They think that there's a difference between trees and nodes, and as a result of that, they build way too complicated abstract data types. And as a result of that, their programs are humongous, and people get the idea that trees are a very difficult thing to work with. But if you understand, as you guys do, that a tree and a node are synonyms, then you will be inoculated against the fear of trees. All right. So why are these things called trees? Well, it's because they look just like a tree in real life. In real life, a tree has roots in the ground, and then it has branches that grow out of the roots. And finally, it has leaves. Right? So a tree looks just like this. That's why it's called a tree. I once got to give this talk in Australia. It was so much fun because the trees do look like that down there. So, as I said, there's no built-in data type called tree in Scheme, and that's because you want different kinds of trees for different purposes. We're going to be looking for most of today and Wednesday at a particular kind of tree that has the property that a node can have any number of children, and there has to be at least one node. So in this world that we're dealing with, there's never any such thing as an empty tree. But other trees are different from that. When we talk about binary trees, for example, it's going to turn out easier to say that there are empty trees. In both cases, we choose what's going to make the programs easier to write. So you'll see after you've written some tree code why no empty tree for a multi-child thing and yes empty tree for binary are the right choices. Okay. Oh, up there is an abstraction diagram where the thing above the line that we're trying to create is this notion of a two-dimensional hierarchy. And the way we're going to implement it is with a constructor make tree. Sometimes you'll hear me say make node. They mean the same thing because trees and nodes. And selectors datum and children. And it turns out datum is just car and children is just cutter in the implementation that we're using. But as with any abstract data type, once we've created this abstraction, you're not supposed to think about it that way. So up here, we have the constructor and the two selectors for trees. And here's our first, above the abstraction barrier, tree program. It takes a tree node and says, is this a leaf? And a leaf node is one that doesn't have any children. Children is a list. It's a plain old linear sequential list whose elements are nodes. So a node doesn't have any children if its list of children is empty. That's what this procedure says. Any questions about that? So leaf question mark doesn't know anything about the implementation of trees, the sort of below the abstraction barrier representation of trees. It uses children, which is the abstract selector for the list of children of a tree, to find out. Now, that list of children, by the way, is not a tree. It's a list, a plain old sequential list linked together by cutters, and cars for the elements, like last week, in which the elements are nodes, are trees, in other words. So it's a list of trees. There's a name for a list of trees. It's called a forest, for obvious reasons. And there isn't any abstract data type for forest, because a forest is just a plain old sequential list. So like all plain old sequential lists, we can use car and cutter to find elements and sublists, respectively. Is there a question? I thought I heard somebody, but I don't see a hand. Okay. 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 So here's T1. One, two, three, four. Five, 6, 7, 8. So this is the list, the tree T1. If I actually print it out in Scheme, it looks like that. But you're not supposed to worry about what it looks like.